March 18th, 1944. Rechlin Testing Center, Mecklenburg-Vorpommern, Germany. The morning air carried the sharp bite of late winter as Oberleutnant Werner Zell walked toward the aircraft that would fundamentally challenge everything he believed about aerial combat survivability. The machine sat on the concrete apron, its substantial bulk unmistakable even at a distance. An American Republic P-47D Thunderbolt, captured intact months earlier, now wore hasty Luftwaffe markings over its original United States Army Air Forces insignia. Yellow paint adorned its undersides and tail surfaces, the standard RLM-04 identification scheme, designed to prevent friendly fire from German anti-aircraft batteries. Zell had flown over 40 different aircraft types during his career as a test pilot at Rechlin. He had evaluated captured British Spitfires and Hurricanes, examined Soviet Yakovlev and Lavochkin fighters, and thoroughly tested nearly every German aircraft in operational service. But the Thunderbolt represented something different. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Combat reports from frontline units described an aircraft that refused to die, that absorbed punishment no German fighter could survive, that brought pilots home despite damage that should have been catastrophic. Today's test would attempt to quantify that survivability through controlled experimentation. The plan was straightforward in concept, but unprecedented in execution. Another Luftwaffe aircraft, a Focke-Wulf FW-190 equipped with cannon armament, would engage the Thunderbolt in mock combat at predetermined altitudes. The attacking aircraft would fire actual 20mm ammunition at the captured American fighter. Live ammunition. Real combat conditions. The only difference was that the test pilot in the Thunderbolt knew exactly when and where the attacks would occur. The objective was not to destroy the aircraft, but to document precisely what level of battle damage a Thunderbolt could sustain, while remaining flyable and controllable. German engineers needed quantifiable data about American aircraft durability to counter combat reports that seemed almost incredible. Frontline pilots regularly described Thunderbolts, returning from missions with entire cylinders shot away from their radial engines, with sections of wing missing, with control surfaces destroyed, yet still under pilot control and capable of reaching friendly territory. Such reports strained credibility among Luftwaffe commanders and aircraft designers who understood that German fighters became uncontrollable or caught fire with far less damage. The systematic testing program at Rechlin existed precisely to separate factual capability from combat exaggeration, to provide engineers and tactical planners with reliable data rather than the fragmentary impressions gathered during the chaos of aerial combat. Zell approached the Thunderbolt methodically, conducting his pre-flight inspection with professional thoroughness despite the aircraft's unfamiliar configuration. The machine was enormous by European fighter standards. The Republic P-47D weighed nearly 10,000 pounds empty, comparable to some light bombers, and substantially heavier than any single-seat fighter currently in Luftwaffe service. The Focke-Wulf FW-190A8, one of Germany's heaviest production fighters, weighed approximately 7,650 pounds empty. The Messerschmitt Bf 109G6 weighed only 5,870 pounds empty. The weight difference was not merely academic. Every pound of aircraft structure represented material, engineering decisions, and design philosophy. American designers had chosen to make their fighter substantially heavier than German equivalents, accepting the performance penalties that additional weight inevitably imposed in exchange for other characteristics that would become apparent during the day's testing. The Pratt & Whitney R2800 double Wasp engine dominated the aircraft's front section, an 18-cylinder radial power plant that displaced 2,800 cubic inches and produced 2,000 horsepower at military power settings. German radial engines like the BMW 801 that powered the FW-190 were considerably smaller and less powerful. The BMW 801D displaced only 1,680 cubic inches and produced approximately 1,700 horsepower. American designers had achieved their power advantage through brute force engineering, larger displacement, higher operating pressures, superior metallurgy, and more sophisticated cooling systems that allowed sustained high-power operation without catastrophic overheating or mechanical failure. The Thunderbolt's engine represented not just superior horsepower, but an entire industrial ecosystem capable of producing precision components at scale, refining high-grade aviation fuels, developing advanced lubricants that enabled reliable operation under extreme conditions. Zell climbed onto the wing root and lowered himself into the cockpit. The interior space was generous compared to German fighters, another consequence of the aircraft's substantial size. American designers had prioritized pilot comfort and visibility over weight savings and minimum frontal area. The instrument panel contained what seemed like an excessive number of gauges monitoring engine parameters that German pilots managed through experience and intuition, rather than constant instrument reference. The cockpit layout reflected a design philosophy that assumed pilots would fly long missions at high altitude in potentially hostile airspace, requiring continuous monitoring of complex systems over extended periods, rather than brief, intense combat engagements close to friendly airfields. Everything about the aircraft's design suggested American assumptions about aerial warfare differed fundamentally from German tactical doctrine. Ground crew assisted with strapping in and connecting oxygen and communication lines. The oxygen system was particularly elaborate, necessary for sustained operations above 25,000 feet, where the Thunderbolt's turbo-supercharger provided decisive performance advantages. German fighters used simpler oxygen systems adequate for shorter-duration intercepts, but insufficient for the extended high-altitude missions American doctrine emphasized. Engine start followed the procedures Zell had learned during earlier familiarization flights. The massive radial engine required specific priming and cranking sequences to ensure proper fuel distribution across all 18 cylinders. When the engine caught and roared to life, it produced a distinctive deep rumble, utterly different from the higher-pitched note of German inline engines or even the BMW radial in the FW190. The sound conveyed power held in reserve, enormous torque available at the throttle's command. Zell taxied carefully, feeling the aircraft's weight through the controls. The Thunderbolt sat high off the ground on long landing gear designed to accommodate a 13-foot diameter propeller while maintaining adequate ground clearance. Visibility over the long nose during taxi operations was poor, requiring frequent S-turns to check for obstacles ahead, a characteristic shared with most powerful single-engine fighters equipped with large radial engines. The runway at Rechlin stretched before him, more than adequate for the heavy American fighter. Zell advanced the throttle smoothly, feeling the R-2800 respond with immediate and progressive power delivery. Acceleration was impressive, despite the aircraft's weight. The turbo-supercharger began spooling up as airspeed increased, its distinctive whine audible even over the engine's rumble. At 75 miles per hour, Zell eased back on the control column. The Thunderbolt lifted off smoothly, its wide-track landing gear providing stable ground handling during the takeoff roll. Positive rate of climb established, gear retraction initiated. The aircraft climbed steadily away from Rechlin, its rate of climb adequate, though not spectacular at low altitude where the turbo-supercharger provided minimal benefit. German combat pilots often criticized the P-47's modest low-altitude performance, comparing it unfavorably to the nimble Bf-109 or FW-190 at medium altitudes, where most combat occurred during defensive intercepts of bomber formations. This criticism reflected genuine performance differences, but revealed incomplete understanding of American tactical doctrine. The Thunderbolt was optimized for high-altitude escort missions, where its turbo-supercharger provided decisive advantages, not low-altitude interception, where naturally aspirated engines performed adequately. Zell climbed to 15,000 feet, the predetermined altitude for the initial test run. Altitude. The turbo-supercharger was fully active, compressing thin air to maintain sea-level manifold pressure and enabling the R-2800 to produce maximum rated power. The performance transformation above 12,000 feet was dramatic. Below 10,000 feet, the Thunderbolt felt heavy and sluggish compared to German fighters. Above 15,000 feet, it became a different aircraft entirely, with excellent speed, surprisingly good acceleration for its weight, and respectable maneuverability, despite its bulk. Radio communication with the FW-190 pilot confirmed both aircraft were in position for the first test sequence. The attacking aircraft would approach from the Thunderbolt's 6 o'clock position, the classic tail attack that German pilots favored when engaging American bomber formations and their fighter escorts. The FW-190 would close to approximately 200 yards, an effective firing range for 20mm cannon, and fire a short burst aimed at the Thunderbolt's fuselage and engine section. Zell held steady course and altitude, fighting instincts honed through years of combat flying that screamed at him to brake and evade. This was a test, not combat. The data required maintaining predictable flight path to ensure proper documentation of damage and effect. German engineers positioned cameras in the Thunderbolt's cockpit and at strategic ground locations to record the engagement from multiple angles. The FW-190 appeared in Zell's mirror, closing rapidly from astern. At 200 yards, cannon fire erupted. Zell saw the muzzle flashes and felt impacts ripple through the airframe, the distinctive crack of 20mm shells striking metal and the deeper thump of explosive charges detonating registered through the aircraft structure. 3 shells struck the Thunderbolt's engine, cowling. 2 more impacted the rear fuselage just aft of the cockpit. The explosive shells detonated on impact, creating the familiar flash and smoke characteristic of 20mm mine shells, the standard German fighter ammunition designed to maximize destructive effect against bombers and their fighters. The Thunderbolt shuddered from the impacts, but continued flying. Zell scanned his instruments rapidly, looking for indications of critical damage. Oil pressure remained steady. Coolant temperature, monitoring the oil cooling system, showed no immediate rise. Engine RPM held constant, manifold pressure unchanged. All indications suggested the Pratt & Whitney R2800 had absorbed direct cannon fire without catastrophic failure. Zell performed gentle control checks, testing ailerons, elevator, and rudder response. Everything felt normal. No unusual vibrations suggested structural damage to control surfaces or their linkages. The aircraft flew as smoothly as it had before the attack, apparently unaffected by battle damage that would have destroyed most German fighters. German fighters used liquid-cooled inline engines, either the Daimler-Benz DB605 series in the Bf-109 or the Junkers Jumo 211 in some bomber interceptors. These engines were more compact than radial designs, enabling sleeker fuselages with reduced drag. But liquid cooling created a critical vulnerability. The cooling system required radiators, coolant lines, pumps, and large volumes of glycol coolant circulating continuously to prevent catastrophic overheating. A single 20mm shell striking a coolant line or radiator would drain the system within minutes. Without coolant, the engine would overheat rapidly, seize, and stop. German pilots knew they had perhaps 3 to 5 minutes of flying time after cooling system damage before engine failure became inevitable. In combat over enemy territory, coolant system damage was effectively a death sentence, forcing immediate emergency landing in hostile territory or bailout over areas where capture or death from ground fire were likely outcomes. The FW-190 engine faced similar vulnerabilities despite being air-cooled. The BMW 801 radial achieved adequate cooling through carefully designed baffles and cowling that directed airflow across cylinder heads. But the system was less robust than it appeared. Battle damage that disrupted cooling airflow or destroyed individual cylinders could cause rapid temperature rise, with overheating leading to power loss and eventual engine failure. The Thunderbolt's R2800 radial engine operated on entirely different principles. Air cooling meant no vulnerable radiators, no coolant lines, no pumps, no liquid that could drain away and leave the engine helpless. Each of the 18 cylinders was individually finned for maximum heat dissipation, projecting into the airstream where cooling air flowed directly across them. More importantly, the engine could continue operating with some cylinders completely destroyed. The R2800's architecture allowed it to function on fewer than 18 cylinders, though with reduced power output. Combat reports from American pilots regularly described bringing damaged Thunderbolts home with 2, 3, or even 4 cylinders, shot completely away. the engine running roughly but still producing enough power to maintain altitude and reach friendly territory. German engineers had heard such reports and dismissed them as exaggeration or propaganda. No engine could function with that much damage. The laws of thermodynamics, mechanical stress, and vibration characteristics made continued operation impossible once cylinder destruction exceeded certain thresholds. The American claims defied engineering principles as German designers understood them. The test program at Rechlin existed precisely to verify or disprove such claims through direct experimentation under controlled conditions. Zell brought the damaged Thunderbolt around for landing at Rechlin, configuring the aircraft for approach and touchdown. The landing was routine. The damaged engine continued producing smooth power throughout the approach and landing rollout. After shutdown, Zell climbed out and joined the engineers who were already examining the battle damage with professional intensity. The damage was immediately apparent and would have been catastrophic on any German fighter. 3 20mm shells had struck the cowling, 2 penetrating into the engine compartment. 1 shell had struck the upper engine cowling at an oblique angle, penetrating the aluminum skin and detonating inside. The explosion had torn a jagged hole approximately 8 inches in diameter through the cowling, exposing the top row of engine cylinders. Fragments from the exploding shell had struck 2 cylinders, gouging deep furrows in the cooling fins and cracking 1 cylinder head. Despite this damage, the engine had continued running normally. The remaining 16 cylinders compensated. For the 2 damaged ones, the engine still producing approximately 85% of its rated power, sufficient for normal flight operations. The second direct hit had struck the engine's reduction gearbox housing, the massive assembly that reduced propeller shaft speed to efficient RPM while the engine spun faster. The shell had penetrated the gearbox housing and detonated, blowing a hole through the cast aluminum structure and destroying several gear teeth on the reduction gearing. Yet the gearbox had continued functioning. American engineers had designed the reduction gearing with substantial safety margins, allowing it to absorb battle damage and continue operating even with components partially destroyed. The gearbox was leaking oil from the damaged housing, but the leak was slow enough that oil pressure remained adequate for continued operation. A German fighter with equivalent gearbox damage would have experienced catastrophic failure within minutes as oil pressure dropped and gearing seized from inadequate lubrication. The fuselage hits aft of the cockpit had penetrated the aluminum skin and detonated inside the aircraft structure. The explosions had torn substantial holes in the fuselage, approximately 12 inches in diameter, exposing internal structure and equipment. Fragments had severed several minor electrical lines and damaged some non-critical hydraulic plumbing, but none of the damage affected aircraft controllability or any essential system. American designers had implemented extensive redundancy in all critical systems. Dual hydraulic systems ensured flight controls remained operational, even with one system damaged. Electrical power came from both engine-driven generator and battery backup. Control cables were routed with separation to prevent single hits from severing both primary and backup connections. German engineers examined the damage patterns carefully, measuring penetration depths, photographing impact angles, and documenting the extent of destruction from each shell. Their analysis confirmed what combat reports had been indicating for months. The Republic P-47 Thunderbolt could absorb battle damage that would destroy any German fighter and continue flying effectively. The implications were professionally disturbing. Luftwaffe pilots engaging Thunderbolts in combat faced an opponent that could survive hits from Germany's most powerful fighter weapons and continue fighting. German pilots knew that a single 20mm shell striking their aircraft in the engine compartment would likely result in forced landing within minutes. They knew their liquid-cooled engines were vulnerable to any damage that compromised cooling systems. They knew their fighters lacked the redundancy and structural robustness to survive battle damage beyond minor strikes to non-critical areas. This knowledge affected tactical decision-making in subtle but important ways. German pilots learned to avoid prolonged engagements with Thunderbolts because even successful attacks that damaged American fighters often failed to achieve kills. The damaged Thunderbolts would withdraw from combat, diving away at speeds German fighters could not match, and limp back to England despite damage that should have been fatal. Meanwhile, any hits German fighters sustained had much higher probability of causing immediate combat loss through engine failure, fire, or structural failure. The exchange rate favored American pilots even when German pilots achieved successful attacks. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Because American aircraft were substantially more likely to survive battle damage and return their pilots safely to base, the test program would continue over subsequent weeks with additional controlled engagements, systematically documenting Thunderbolt survivability across different attack profiles and damage scenarios. But the fundamental conclusion was already apparent from this initial test. American engineers had designed the P-47 Thunderbolt with survivability as an explicit primary design objective, accepting weight penalties and performance compromises in exchange for unprecedented ability to absorb battle damage and protect the pilot. The contrast with German design philosophy could not have been more stark. German fighters prioritized performance over survivability, keeping weight minimal to maximize speed and climb rate and maneuverability. This philosophy made tactical sense when Germany was on the offensive, when combat occurred over friendly territory, when damaged German pilots could belly land in German-held fields and return to combat quickly. But by 1944, the strategic situation had reversed completely. Combat occurred over Reich territory as Allied bombers struck deep into Germany, but German pilots who suffered battle damage had nowhere safe to land. The entire country was becoming hostile territory as Allied forces advanced, and German infrastructure collapsed under sustained bombing. A damaged German fighter forced to land might be destroyed by roving Allied fighters, strafing airfields, or land at a base that had been bombed hours earlier and lacked repair facilities or spare parts. American pilots who suffered similar damage could nurse crippled aircraft back across the Channel to England, where extensive repair facilities and unlimited spare parts and skilled mechanics would restore damaged fighters to service within days. The cumulative effect of these differences in aircraft survivability and logistical support was devastating to German fighter effectiveness. Werner Zell flew the damaged Thunderbolt 3 more times over the following week, each test pushing the boundaries of survivability documentation further. The second test involved attacks targeting the wing structure, attempting to determine whether the Thunderbolt's thick wings could withstand battle damage while maintaining structural integrity and controllability. The FW-190 pilot fired controlled bursts into the Thunderbolt's port wing at predetermined locations. 6 20mm shells struck the wing, 3 impacting the main spar area, and 3 hitting the outer wing panel. The explosive shells detonated on impact, tearing irregular holes through the aluminum skin and damaging internal structure. American designers had built the Thunderbolt's wings with substantial structural margins. The main spar was massive compared to German fighter designs, constructed from heavy aluminum extrusions with extensive reinforcement. The wing carried 850 caliber machine guns, 4 per wing, mounted outboard of the fuselage. Ammunition boxes, gun mechanisms, and associated equipment added substantial weight, but also contributed to structural strength through distributing loads across multiple hardpoints. When 20mm shells struck the wing structure, they created localized damage, but did not compromise overall structural integrity, because load paths redundantly distributed stress throughout the wing's robust framework. Zell performed aggressive maneuvers after sustaining wing damage, testing whether battle damage affected handling or control response. He executed high G-turns, maximum rate rolls, and rapid pull-ups, loads that would stress even an undamaged wing. The Thunderbolt responded normally. No unusual vibrations indicated impending structural failure. The damaged wing continued carrying its share of aerodynamic loads without failure. German fighters built to lighter weight standards could not have survived equivalent wing damage. The Bf-109's wing structure was optimized for minimum weight, with thin skins and closely spaced ribs, providing adequate strength for normal operations, but minimal safety margins for battle damage. A 20mm shell penetrating a Bf-109 wing near the main spar had high probability of causing catastrophic structural failure during high G maneuvering. German pilots knew their aircraft's limitations intimately. They knew aggressive maneuvering after sustaining wing damage risked structural failure and fatal crash. They knew their fighters were built to minimum acceptable standards to save weight and enable production of maximum numbers with limited resources. This knowledge affected combat tactics in ways difficult to quantify, but operationally significant. The third test examined tail section survivability, focusing on whether the Thunderbolt could maintain controllability after battle damage to control surfaces. The attacking aircraft fired at the Thunderbolt's empennage from astern, the standard pursuit curve engagement German pilots favored. Multiple 20mm shells struck the horizontal stabilizer, vertical stabilizer, and rudder. The damage was extensive and immediately visible. The rudder took 3 direct hits, explosive shells tearing large irregular holes through the fabric-covered control surface and partially destroying the internal metal framework. Nearly 40% of the rudder's surface area was simply gone, blown away by exploding cannon shells. German fighters with equivalent rudder damage would have become uncontrollable in yaw, unable to maintain coordinated flight or execute controlled turns. The Thunderbolt continued flying normally. Zell tested rudder authority carefully, initiating gentle yaw inputs and gradually increasing deflection angles. Rudder response was reduced compared to undamaged condition, but remained adequate for controlled flight. The aircraft could maintain coordinated flight, execute controlled turns, and perform all normal flight maneuvers despite losing nearly half the rudder surface. American designers had created control surfaces with substantial area margins, sized larger than minimum requirements to provide safety factors for battle damage. The Thunderbolt's rudder was approximately 30% larger than would be needed for basic directional control. This excess area meant the aircraft retained adequate control authority, even after losing significant portions of control surface to battle damage. The horizontal stabilizer took 4 direct hits, shells detonating and tearing holes through both the fixed stabilizer and the movable elevator control surface. German engineers expected this damage would compromise longitudinal control and make the aircraft dangerous or impossible to land safely. Zell performed careful flight testing, exploring the damaged aircraft's handling characteristics systematically. Pitch control remained effective despite visible damage. The elevator responded to control inputs with slightly reduced authority but adequate effectiveness for all normal flight conditions. Zell executed approaches and go-arounds, testing whether the damaged elevator provided sufficient control for landing. The aircraft handled well, requiring only minor compensation for slightly heavier control forces. The landing was routine. The damaged Thunderbolt touched down smoothly, maintained directional control throughout rollout, and responded normally to brake application. After shutdown, German engineers swarmed over the aircraft, documenting and photographing the extensive tail damage that had failed to significantly degrade aircraft controllability. The test program's final phase examined the most critical vulnerability for any combat aircraft, the pilot himself. No amount of structural robustness or system redundancy could prevent combat loss if the pilot was killed or incapacitated by battle damage. German fighters provided minimal pilot protection, relying primarily on armored headrest and small armor plate behind the pilot's seat. The Thunderbolt surrounded the pilot with protection unprecedented in single-seat fighter design. The cockpit incorporated armor plate totaling nearly 300 pounds, positioned to provide comprehensive protection from most attack angles. Behind the pilot's seat sat a thick armor plate, measuring approximately 3/8 of an inch thick, sufficient to stop rifle-caliber bullets and shell fragments, though not direct hits from 20mm cannon. Additional armor protected the pilot from below, critical shielding against ground fire during low-altitude attack missions. The floor beneath the pilot's feet incorporated armor plate that would stop 50-caliber bullets and most small arms fire. Side armor plates protected the pilot's torso from oblique attacks. The windscreen incorporated thick, bulletproof glass, capable of stopping 50-caliber ammunition. German engineers carefully measured and weighed all armor components, documenting their thickness, coverage area, and estimated protective capability. The weight devoted to pilot protection exceeded the total empty weight of some German light fighters. American designers had accepted a 300-pound weight penalty solely to enhance pilot survivability, reducing aircraft performance in exchange for dramatically improved pilot protection. The philosophy reflected fundamental American advantages in industrial capacity and resource availability. The United States could afford to build heavier, more protective fighters because American factories produced aluminum, steel, and aviation components in quantities that made weight penalties acceptable. Germany faced chronic shortages of aluminum and steel, forcing designers to minimize weight everywhere possible just to maintain adequate production numbers. More significantly, the armor reflected different valuations of pilot life. Training a replacement fighter pilot required approximately 6 months and substantial resources: fuel for training flights, ammunition for gunnery practice, instructor time, and aircraft wear from training operations. American training programs could absorb these costs because fuel, ammunition, and instructor pilots were available in adequate quantities. Germany, by 1944, faced severe fuel shortages that forced reduction of pilot training time from over 200 hours to fewer than 100 hours by war's end. New German pilots arrived at operational units with dangerously inadequate experience, making them vulnerable to experienced Allied pilots flying superior aircraft with better protection and support. Losing an experienced pilot meant losing accumulated combat knowledge, tactical expertise, and hard-won skill that required months or years to develop. American designers understood this reality and built aircraft intended to maximize pilot survival, even at cost of some performance capability. The 300 pounds of armor in a Thunderbolt represented insurance policy protecting valuable trained pilots who could continue fighting if they survived being shot down. German pilots who flew captured Thunderbolts consistently commented on the sense of security the extensive armor provided. Werner Zell noted in his test reports that flying the Thunderbolt felt qualitatively different from flying German fighters: less exposed, more protected, with confidence that the aircraft would absorb damage and bring him home despite battle damage that would have killed him in a Bf-109 or FW-190. This psychological factor had tactical implications difficult to measure but operationally significant. American fighter pilots could press attacks more aggressively, knowing their aircraft would likely survive hits that would be fatal in lighter fighters. They could accept calculated risks that German pilots avoided because German fighters offered minimal protection and unforgiving performance characteristics that made battle damage likely fatal. The confidence inspired by robust aircraft design and comprehensive pilot protection contributed to American tactical aggressiveness that German pilots increasingly found overwhelming during 1944-45. The test program documentation included detailed technical reports with extensive photography, damage diagrams, and performance measurements taken before and after battle damage. These reports circulated among German aircraft designers, tactical planners, and operational commanders, providing authoritative data about Allied aircraft capabilities. The conclusions were professionally documented and brutally clear. The Republic P-47 Thunderbolt could survive battle damage that would destroy any operational German fighter. The aircraft's robust construction, redundant systems, reliable air-cooled engine, and comprehensive armor protection combined to create unprecedented survivability that fundamentally altered the tactical calculus of aerial combat. German designers understood the engineering principles that enabled Thunderbolt survivability. The solutions were not mysterious or beyond German technical capability. Building fighters with heavier structures, more extensive armor, redundant systems, and robust engines was entirely possible given adequate resources and industrial capacity. But Germany, by 1944, lacked those resources. The aluminum required to build Thunderbolt-style heavy fighters was not available in sufficient quantities. Steel for extensive armor plate was allocated to tanks, artillery, and industrial machinery. The sophisticated machine tools needed to manufacture robust radial engines were scarce and increasingly vulnerable to Allied bombing. Even if German designers created plans for heavily armored, robustly constructed fighters, German factories could not produce them in meaningful numbers while simultaneously producing all other military equipment the Wehrmacht required. The captured Thunderbolt testing program thus revealed a truth more fundamental than simple aircraft performance comparisons. By 1944, Germany could not win the air war over Europe regardless of tactical innovation or pilot courage, because the underlying industrial competition had already been decisively lost. The United States produced aluminum in 1944 at rates exceeding total German aluminum production by factors of 4 or more. American steel production exceeded German capacity by similar margins. American factories manufactured aviation engines, both radial and inline types, in quantities that dwarfed German production, while simultaneously maintaining quality and incorporating design improvements based on combat experience. The industrial mathematics were unforgiving and ultimately decisive. Werner Zell continued his test pilot career through the final year of the war, flying numerous captured Allied aircraft and providing professional technical assessments that documented enemy capabilities with accuracy and objectivity. He survived the war and later provided extensive debriefings to American intelligence services about German testing programs. His reports about Thunderbolt survivability testing confirmed what American engineers had intended when they designed the aircraft. The P-47 was built to bring pilots home, to absorb battle damage without catastrophic failure, to provide comprehensive protection through robust engineering rather than minimum weight optimization. The design philosophy worked exactly as intended, providing American pilots with aircraft that could survive conditions fatal to opponents. The captured Thunderbolt, tested at Rechlin, remained in German service through early 1945, used primarily for demonstration flights and continued technical evaluation. As Soviet forces advanced westward, Rechlin was evacuated, and the captured Allied aircraft were either destroyed to prevent recapture or abandoned as German forces withdrew. The specific fate of the Thunderbolt, tested by Werner Zell, is not definitively documented, likely destroyed during the final chaotic months of the war. The broader significance of the survivability testing extended beyond immediate tactical implications. The program demonstrated that professional, military organizations could accurately assess enemy capabilities even under desperate strategic circumstances. German engineers and test pilots provided honest, objective evaluation of Allied aircraft, neither exaggerating enemy capabilities through defeatism nor minimizing them through wishful thinking. Their reports documented uncomfortable truths about German disadvantages with clinical precision. This professional competence in intelligence assessment, maintained even as Germany faced inevitable defeat, represented military professionalism in its highest form, separating factual capability assessment from political ideology or strategic desperation. The lesson German pilots learned from flying captured Thunderbolts was ultimately a lesson about industrial capacity applied to military equipment design. The nation that could afford to build fighters 3,000 pounds heavier than necessary, that could devote 300 pounds to pilot armor, that could accept performance penalties in exchange for redundancy and survivability, that could produce such aircraft in quantities of 15,000 units, possessed industrial advantages that rendered tactical excellence increasingly insufficient to alter strategic outcomes. American factories during 1944 produced over 100,000 aircraft of all types, while simultaneously manufacturing tanks, artillery, trucks, ships, and all other military equipment required for global war. German production during the same period, despite heroic efforts and increasingly desperate improvisations, never exceeded 40,000 aircraft annually, and even this reduced figure came at cost of quality degradation and delayed introduction of advanced designs. The Republic P-47 Thunderbolt, examined in minute detail by German engineers at Rechlin, represented visible manifestation of this industrial superiority. Every rivet, every redundant system, every pound of armor plate, every cubic inch of engine, displacement testified to American resource abundance and industrial capacity operating at scales German planners could not match. The test pilots who flew the captured Thunderbolts and experienced firsthand its unprecedented survivability understood with professional clarity that they faced opponents equipped with fundamentally superior tools produced by fundamentally superior industrial systems. This knowledge, accurately gathered and professionally documented, arrived too late to change strategic outcomes. By the time Werner Zell was testing the Thunderbolt's survivability at Rechlin in March 1944, the outcome of the air war over Europe had already been determined by industrial mathematics. No amount of German tactical skill or engineering innovation could overcome. The captured Thunderbolts, wearing hasty German markings, represented not just individual aircraft, but rather complete industrial ecosystems capable of designing, producing, and logistically supporting thousands of complex weapons systems simultaneously, while maintaining quality and continuously improving designs based on combat experience. The ability to build fighters that could survive direct hits from 20mm cannon and bring pilots home, despite catastrophic damage, represented luxury available only to nations with industrial capacity so vast that weight, penalties, and performance compromises became acceptable trade-offs for enhanced survivability. Germany attempted to compete in this industrial war with a fraction of Allied resources, declining access to strategic materials, and infrastructure increasingly degraded by sustained bombing. The professional competence of individual German engineers and pilots could not overcome these fundamental imbalances. The test program at Rechlin provided accurate intelligence about Allied capabilities, but intelligence alone could not conjure the aluminum, steel, machine tools, skilled workers, and undamaged factories needed to build competitive aircraft in adequate numbers. The story of German pilots flying captured Thunderbolts and confronting the aircraft's shocking survivability thus becomes a microcosm of Germany's broader strategic situation during the final years of World War II. Professional military excellence, accurate intelligence gathering, and tactical innovation proved insufficient when facing opponents with overwhelming material advantages, systematically applied through competent execution. The Thunderbolt's ability to survive direct 20mm cannon hits represented not mysterious technology or incomprehensible engineering, but rather the straightforward application of adequate resources to aircraft design, problems without the crushing resource constraints that limited German options. When nations with adequate industrial capacity chose to build fighters optimized for survivability rather than minimum weight, they produced aircraft like the P-47 Thunderbolt. When nations with inadequate resources attempted to compete through tactical excellence and engineering innovation alone, they produced capable fighters in insufficient quantities with inadequate survivability characteristics. The uncomfortable truth that German test pilots confronted at Rechlin in 1944 was that courage, skill, and professional competence, qualities the Luftwaffe possessed in abundance, could not overcome industrial disadvantages measured in ratios of 4:1 or 5:1 across virtually every category of military production. The lesson was professionally documented, accurately reported, and strategically useless because the resources needed to implement solutions did not exist and could not be created, given Germany's deteriorating strategic position. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.